Our last presentation for today is going to be by Cian Desmond from Loughborough University, and he's going to be going into those details that we were just hearing about, so the flow over the canopy and how the canopy details affect that. And so, Cian, please go ahead.
Thank you. Good afternoon. Thanks very much for the introduction. So this is a piece of work that was undertaken as a collaboration between Loughborough University in England and Orleans University in France. And what we were looking at is the role that canopy morphology can play in improving CFD simulations in forested terrain. So just to kick things off, let's imagine this is some notional site where we're looking at the wind resource and we're asked to carry out a wind resource assessment. So what we do is we'd isolate the areas of forestry and include this within the CFD as a porous subdomain. Now, as the wind moves into this porous subdomain, it's met by a resisting force acting in the opposite direction. And this is modeled in the Rand's equations by including this term as a momentum sink. There's also going to be a production of kinetic energy inside the porous subdomain and a dissipation of kinetic energy. Now, these equations appear in different forms, but this is the form that we're using. And most of those terms and variables are probably going to be familiar to most of you, except perhaps this AZ term. That's the leaf area density. And what that does, it describes the vertical profile of the canopy, the vertical structure of the canopy. So let's see how that's actually derived. So let's take this as a little forest. Let's take a horizontal cross-section through it. So we're going to calculate the leaf area density at a certain height, Z. So we take a horizontal cross-section at the height Z, and then the leaf area density is a total one-sided leaf area within this box. So what that is the number of leaves multiplied by the area of a single face of the leaf, and that's divided by the total volume of the box. So that's meters squared divided by meters cubed, so the unit of leaf area density is per meter. And if we take a number of different horizontal sections at a number of different heights, we build up a leaf area density profile, which might look something like this for this particular little forest. So rather than going out and counting all the leaves in the forest, there's easier ways of coming up with a leaf area density profile. There's textbook values. These are published values that are in the literature for what kind of leaf area density profile you'd expect for different types of forests. There's also winter litterfall collection. So this is going out in the winter, marking off a number of control areas, collecting the leaves inside that area and counting the leaves, quite labor intensive. There's also this little tool, which is called a densiometer. So it's essentially a concave mirror with a number of markings on it. And you can see there's a little bubble there for keeping it level, just over here. And what you do with that is essentially stand at a number of locations within the forest, level it up, and the image on the mirror there gives you an idea of the density of the forest. Moving on to more sophisticated methods, this is a LAI 2000. It uses a very similar method to the little densiometer above, but it uses optics and computer processing rather than just looking at the image in the mirror. One of those costs about €8,000, so not a whole pile of money. There's also a LiDAR survey. So this is a standard piece of a surveying kit these days. It's like a total station, and you do a sweep of the canopy with this laser, and you build up a very clear, very detailed picture of the canopy structure. There's also aerial LiDAR systems, very similar idea, but deployed from the air. This one is in some kind of a microlight. And using these two last methods in particular, we get a really clear level of detail of what's going on in the forest, so down to a leaf-by-leaf level of detail. So the question that we're asking in this piece of research is this actually beneficial? So the validation data that we're using, as I mentioned, this is a collaboration with Orleans University, and some of you may be familiar with the work of Sandrine Auburn. And she carried out some experiments for us in the Lucien-Malevard wind tunnel. So it's actually in this secondary test section over here. So it's a 5 meter by 5 meter by 12 meter long wind tunnel, so quite a large atmospheric boundary layer tunnel. And it's got a maximum operating wind speed of about 10 meters per second. We're operating down about 4.5. This is the view inside the tunnel. You can see at the back here, we've got a turbulence grid. So this is generating the atmospheric turbulence. Down the bottom, you can just about see the Irwin spires, and there's a rough metallic floor. So all these things are generating an atmospheric boundary layer, a simulation of an atmospheric boundary layer. And the measurements are taken using stereoscopic PIV. So you can see we've got two cameras positioned looking at our little forest. I'll talk a little bit more about the little forest later on, but it's 100 architectural model trees of various shapes and sizes. I'll talk a little bit more about that later on. And the air is seeded with olive oil. So there's a very fine mist of olive oil in the air. And then there's a laser plane which is fired down, which illuminates the little bits of olive oil. and then we get a very clear picture of what's going on with the flow. So this is the output from the stereoscopic PIV. So as you can see, it's the kind of level of detail that you'd expect from a CFD simulation. So it's really beautiful data to work with when you're validating your CFD models. So the data that we actually have available is the mean U, V, and W. So with stereoscopic PIV, you get the wind direction in the three directions, rather than just U and V, you get the three directions, and also the variance in the three directions. So it's really high quality data. So these little architectural model trees, so they're made out of etched brass, and there's a etched brass wire, and there's ground silicone to simulate the foliage. So we've done a number of experiments with these little trees, and in this particular experiment, we've got 100 different ones of all different shapes and sizes. The mean height is about 80 millimeter, but they vary wildly. So to represent this little tree in our CFD, what we do is we take 8 high-definition pictures of each tree. This is then converted to a black and white image, which is fed into a piece of software called Tree Analyzer, which produces a 3D virtual canopy. From this, we can then extract the leaf area density profile, the AZ, so showing how the vertical profile varies with height. And this gives us all the information that we need to model this little tree in our CFD with the source and sink terms. And that's just an image of a little ISO surface behind this tree. And so ANSYS TFX is the CFD solver we're using. We're using version 14.0. We're using a RANS configuration, so that's a steady state solution, and the SST turbulence model. Just to give you an idea of the size of the domain, there's about 6.7 million cells, and we aimed for about 10 cells beneath the canopy height in each of the simulations. So let's look at some results. So in the paper that we're going to be providing for this, we used 7 different metrics to compare the data. There's a whole pile of data there. From the PIV measurements, we got a total of 43,200 measurement points, so it's a lot of data. So we use these metrics to compare them. And on this one, I'm just going to show the correlation coefficient, because it's probably what most of you are familiar with. So here we're comparing the mean wind speed in the CFD compared to the mean wind speed in the tunnel. So the first way we represented the canopy in the CFD was just using a simple porous block. There's not much canopy detail in there. And the first leaf area density that we used was just the mean leaf area density. So this is averaging the leaf area density in X, Y, and Z to give us a single value, which we then applied throughout the whole little porous block. The next step of detail was including the full leaf area density profile. So here it's averaged in X and Y and allowed to vary in Z. We then modeled the canopy by letting the roof of it vary in height to reflect the actual structure of the canopy. And again, using the mean of the leaf area density, this is just one single value applied throughout the whole domain. And then also the full leaf area density profile, again, average in X and Y, but varying in Z. And then the final level of detail we went to was we modeled each tree as a little individual cylinder. So this is quite labor intensive to set up, as you can imagine. So first off, the mean of the leaf area density, so again, average in X, Y, and Z, and then allowing it to vary in the Z direction. And then the final level of detail we went to was to use 10 by leaf area density profile. So as I mentioned, we've got trees of all different shapes and sizes within our little forest, but broadly speaking, there's 10 categories of tree. So this is varying from tall and wide to short and narrow, as you can see in the image there. So for each category of tree, we calculated a different leaf area density profile and made this active within its appropriate cylinder. So we were a little bit disappointed with these results in that we were hoping that we went to the effort of modeling each tree individually that we get really high correlation, but as you can see, that's not exactly the situation. But what this does show is that the leaf area density is quite crucial, and if you can get a really appropriate value for the leaf area density and get the variation included there, it really improves your simulation results regardless of the actual geometry that you're using. And it's also worth mentioning that moving from this porous block up to number of cylinders is extremely computationally expensive. It increases the computation time by about 30%, whereas including this extra leaf area density profile information is negligible increase in the computational expense. So just to look at how good things can get, we're just going to look at this simulation with the 10 different leaf area density profiles. And this is the output from the CFD. So on this plane, we've got data for both the CFD and the wind tunnel. So there's 43,000 points in there. And we're going to look at values for velocity on the left and turbulent kinetic energy on the right. So the CFD will be appearing as a red line and the wind tunnel as a blue dot. So all of this data is non-normalized. So it's the actual information that came out from the wind tunnel compared to the actual information from the CFD. There's no normalization going on there. So firstly, the inlet. So you can see the wind speed profile is matching very well before it hits the tree. The turbine kinetic energy is a little bit lower in the CFD. We did try adjusting that to get them to match perfectly, but then that causes some instabilities within the domain. So we just left it at that. It's within a few percent. And then just behind the little miniature forest, so this is a distance of HC. HC is the mean canopy height, in this case about 80 millimeters, or at a scale of 1:300 here. So that's the profile at HC, 2 HC. I don't have a whole pile to say about these, but I'll move through the pictures. 5, 6, 7, 8 HC, 9, 10, 11, and 12. So I guess we're getting really nice correlation as we move downstream of the forest. We're particularly happy with the values for the turbine kinetic energy here, because as I said, we're using a RAN simulation, which is steady state, typically not very good at capturing these turbulent fluctuations, but as you can see, it's doing quite a good job. Also, the CFD wind speed profile is lagging the wind tunnel by a small amount there. We could tune that out by adjusting the drag coefficient, the CD term, or indeed adjusting the leaf area density profile to get those to match up perfectly. But we wanted to resist the urge to tune anything here. We just wanted to kind of use CFD as much of a black box as possible and just let the models stand in their own merits. What we don't see in this image is where the wind speed profile recovers. This is the inlet value. So as you can see at 12 HC, it's still quite off what was at the inlet. So the flow is still perturbed by the presence of the forestry. So let's just zoom out a bit. So this is the turbulent kinetic energy data from the CFD. So you can see the bubble of turbulent kinetic energy spreading away from the forest there. And 12 HC is the last point at which we have validation data. So the rest of it, we're just kind of assuming that the CFD is doing a good job. What I've added in here is just a little ISO surface. So this is the ambient turbulence level plus 25%. So this is kind of where, within 25% of the ambient level, we're just kind of saying that the turbulence from the forest has been washed out at this stage. And it's extending to about 40 HC behind the last tree. So if you get to the last tree, you move 40 HC back, so that's quite far. And about 4 HC above the ground at that point. Just to look down and plan. So this green line outlines the footprint of the forest, let's say. So it's 9 HC across and also 9 HC in the other direction. And you can see there this little bubble of turbulence spreads about HC around each side and then kind of tails off quite quickly. So just some conclusions. So firstly, OS maps can be misleading. This is the OS map that we had at the start of the presentation. And if we take a look at a simple aerial photograph, we can see that this forested area in the north is actually devoid of any forest, and this one in the south is quite patchy. So obviously there's seasonal, annual, and forest management variations going on there, so we should really be taking account of those. As we saw, the correct leaf area density profile is more important than getting the geometry right. Luckily, cheap, effective tools exist to accurately measure the leaf area density. These things like the LAI 2000 and this LiDAR system. Also, there's no significant increase in computation time by including the full leaf area density profile, as we saw. And finally, tuning of LAD to match observations can cause issues. So this is something that sometimes happens in industry, where you pick your leaf area density profile based on what's published in the textbooks, and then adjust it until your CFD is singing the same song as your field measurements. But the problem here is that it's not clear what effects you're tuning out, and one cause for concern we'd have is stability. So we had a paper at the Torque conference in Oldenburg there recently, looking at stability in forested terrain, and we saw something similar today. And essentially what the outcome of that was that non-neutral conditions occur in forested areas up to about 30% of the time at wind speeds below 10 meters per second. So that could be a cause for concern. So this is a project in which I'm involved. It's called WADIT. It's a European collaboration project, and there's 17 of us across Europe, and we're all working together to increase the predictability of wind energy. Thank you very much. If you want to get in touch, I've got a profile on Links FM, so it's linksfm/Cian, and you can see all my contact details there. Thank you very much.
So thank you, Cian, for leading us through the details of the canopy flow modeling. And do we have questions on that? David again.
Yeah, David Hilbert from Repower again. I have two questions. In fact, one is, did I understand it correctly on the slide with the velocity correlation?
Yep.
That your best model in the end was the one with 10 times LAD?
Yep.
But I think the second or third best was having just a uniform height and a uniform LED.
That's correct, yeah.
Okay, because I was surprised actually by
Me too,
the small increase in improvement.
And just, oh sorry, go ahead, yeah.
No.
Yeah, just to mention as well, but we compared it with 7 different seven different correlation metrics which are discussed in the paper, and we got the same trend for each metric. So yeah, it's quite surprising how low the improvement was by including the varying roof. Yeah.
I agree, although it is in line with findings from myself also in this area. And my second question is, are you planning to roll this out in the field? Because I've seen many studies on forest with CFD compared to wind tunnel studies that matched quite well or showed a very good performance. And then out on the field, performance was less good.
Impressive.
So is there anything planned in that direction?
Well, we're on the hunt for data. I got 8 months left to my PhD, and we've got a couple of sites that were supplied by Eric Dupont, the EDF, and there's a second site that I can't, the name of it doesn't come to mind, and that's something that we're potentially looking at, because we have the wind speed data, but what we don't have is the canopy data. But as I mentioned to Tomas earlier on, this level of detail that we have in the wind tunnel is second to none, really. You know, like there's so many data points there, so to replicate that in the field is going to be very expensive.
I know, yeah.
But yeah, I agree with you. That's in the last 8 months of PhD, we definitely want to bring this into the real world. So yeah, thanks for the question.
Looking forward to it.
Just to mention as well, you said there that the variation in the canopy height wasn't so important. We actually use that variation in canopy height data to calculate the mean of the leaf area density profile within the pore subdomain. So even though that height data hasn't been explicitly used, it is being used in the calculation. So I think it could still be quite useful.
Thanks.
Thanks.
Okay. We've got another one over here, Mark.
Hi.
Hi, Mark.
Hi. You showed a very impressive match with the TKE.
Yep.
And letting the model stand on its merits, as you say. I wonder, you stuck in these drag forces into the K epsilon, well, SST with SST terms. You didn't have to do any tuning or tweaking?
No,
of the
we used
constant
values that were published in a paper by Engelou 2009. I can give you a copy of that, where he used these similar trees. And he used 5 different ones. So there was kind of ones like what I showed you there. There's also conifers, and there was also a winter tree with no foliage on it. And he proposed values, and so we stuck to his values. But if we were to tune that CD value, we could improve the correlation even further. But we just wanted to let the models stand on their own merits rather than tuning things. Because if you tune one, he's going to do the best for you. You know. So yeah. So it's yeah.
Okay, so you used SST without having to do anything extra as far as the drag force?
Yep, just with the leaf area density profile. Yep, that's it.
Okay, I think we've got one last question over here. Just over here.
Hello. How high is your wind tunnel in relation to the trees? Because I've seen wind tunnel measurements where wind tunnel was too shallow, so it affected the quality of the measurements.
Yeah, so the height of the wind tunnel is 5 meters high, and our little trees are about 100 millimeters high. So, yeah. So that's good for a boundary layer configuration, because obviously it's more like what we got in the real world.
Okay, thank you, Cian.
Thank you.
Thanks for that presentation.
Cheers.